I'm gonna type that shit twice. Oh, why didn't it count? There we go. Of course, it is unfortunate that one must learn the elements of a new language to master some mathematics. But one could, with much justice, complain that the French people insist on their language, the Germans on theirs, and so on. Obviously, English is the best language, and the French and the Germans are exhibiting provincialism by insisting on holding on to their respective languages. The language of mathematics has the additional merits of being universal. There are justifiable criticisms on the symbolism of algebra, although they are hardly major ones. Mathematicians are greatly concerned about the accuracy of their reasoning, but pay little attention to the aesthetics of appropriateness of their symbolism. Very few symbols suggest their meaning. The signs plus, minus, equal, and the square root are easy to write, but they are historical accidents. No mathematician has bothered to replace these by at least prettier ones, perhaps a diamond for plus. The 17th century mathematician Gottfried Wilhelm Leibniz, who did spend days on the choice of symbols in an effort to make them suggestive, was an exception. There are even inconsistencies in symbolism which, once recognized, fortunately do not impair their clarity. For example, when two letters such as AB are written together with no symbol between them, then it is understood that multiplication is meant. However, two numbers such as 3 and a fraction 1/2 with no symbol between them means 3 plus 1/2. Symbolism entered algebra rather late. The Egyptians, Babylonians, Greeks, Hindus, and Arabs knew and applied a great deal of algebra, which we learn in high school, but they wrote out their work in words. Their algebraic style is in fact called rhetorical algebra because, except for a few symbols, they used ordinary rhetoric. Rhetoric. It is significant that symbolism entered mathematics in the 16th and 17th centuries, when pressure to improve the efficiency of mathematics was applied by science. The idea of using symbols was no longer new, but mathematicians were so undoubtedly stimulated to extend the application of symbolism and to adopt it readily. Exponents. One of the simplest examples of the convenience of algebraic symbolism or algebraic language is found in the use of exponents. We have already used frequently such expressions as 5 squared. In this expression, the number 2 is an exponent and 5 is called the base. The exponent is placed above and to the right of the base to indicate that the quantity to which it applies is 5. 5 in this example is to be multiplied by itself, so that 5 squared equals 5 times 5. Of course, there would be no great value in the use of exponents if their use were limited to such instances. Suppose, however, that we wish to indicate 5 times 5 times 5 times 5 times blah 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 blah. Okay, so here 5 occurs 6 times, so you would write that as 5 to the exponent of 6. That is, when the exponent is a positive whole number, it indicates how many times the quantity to which it is applied occurs as a factor in the product and this quantity and itself. In such instances as 5 to the exponent of 6, the use of exponents saves a lot of writing and counting of factors. Exponents are even more useful than we have thus far indicated. Suppose we wish to write a bunch of whatever. It's going to be 5 to the exponent of 6 times 5 to the exponent of 4. Moreover, the original product calls from 5 multiplied by itself to a total of 10 factors. This can be written as 5 to the exponent of 10. We see, however, that if we add the exponents in 5 to the exponent of 6 plus the exponent 5 to the exponent of 4. 6 plus 4 will get you 10. Therefore, you're going to have 5 to the exponent of 10. Both answers are correct. More generally, when m and n are positive whole numbers, m and n being the exponents in the equation, so now we're getting more abstract, where instead of it being 5, we're going to substitute it using a, and the exponent is going to be either m or n. So if two exponents are multiplied, if you have two bases that are multiplied, the result will be that the exponents are added. Okay, for example, if you have, oh, wait a minute. Yeah, that was the example. Okay, yeah. Okay, this statement is really a theorem on exponents. Its proof is trivial. All that the theorem says is that if one quantity contains a as a factor m times, and another quantity contains a as a factor n times, the product of these two quantities contains a as a factor m plus n times. And now suppose we wish to write 5 to the exponent of 6 divided 5 to the exponent of 4. Moreover, if you have the exponents and you want to divide, basically you're going to subtract. We can now obtain the same results in that equation. We can subtract the 4 from the 6 and so arrive at 5 squared. Here too, as in the case of multiplication, the exponents keep track of the number of 5s, which occur in the numerator and denominator, and the subtraction of the 4 from the 6 tell us the net number of 5s remaining as factors. In more general language, we can say that if m and n are positive whole numbers, and if m is greater than n, then same thing. am divided by an equals a to the exponents of m minus n. This result too is a theorem on exponents, and the proof is again trivial, but because of all the theorem states is that if we cancel the a's common to the numerator and denominator, we shall have n minus n factors left over. We might find that we have to deal with the exponents. So we have I see. Okay. So now what if we flip it? Now we have 5 to the exponent of 4 divided with 5 to the exponent of 6. This time, if we cancel the 5's common to the numerator and denominator, we are left with 5 occurring twice in the denominator. That is, we are left with a fraction of 1 divided 1 over 5 times 5 equals 1 over 5 squared. We can obtain the results at once by subtracting the exponent 4 in the numerator from the exponent 6 in the denominator. In general form, we have the theorem. If m and n are positive whole numbers, and if n is greater than m, then we have the said equation. There is a possibility of encountering both the exponents are the same, so like 5 to the exponent of 4 over 5 to the exponent of 4. It would be nice to be able to simplify this expression too by using exponents. However, here, unlike the two previous cases, the two exponents are equal. If we were to say subtract the exponent 4 of the denominator from the exponent 4 of the numerator, we would have 5 to the exponent of 0. Now, 5 to the exponent of 0 has no meaning. However, we know that 5 to the exponent of 4 over the 5 to the exponent of 4 has a value of 1. If we agree to give a meaning to a 0 exponent, and in fact agree that a number to the zero exponent is to be 1, then we can use the symbol 5 to the exponent of 0. Further, with this meaning, we can properly write 5 to the exponent of 4 over 5 to the exponent of 4 equals 5 to the exponent of 4 minus 4, which equals 5 to the exponent of 0, which in total equals 1. Okay, should be easy. So it just needs to be in a fraction, that's all. So we have n minus m instead of m minus n. Oh, excuse me. So this one will probably just end up being a fraction. So I can assume this one, I usually don't do math questions on stream, but I just want to test this out real quick. Because it should be stupidly easy. This should be 1 over 5 to the exponent of 3, if I'm not mistaken. Hope that's correct. And that doesn't even look like a 3. That looks like a fucking 7. Give me that 3. Make you a 3. There we go. Let's explain it. 3. Hold up. Hold up. Yeah, we have that. And that. Yeah. Yeah, okay. I think I got it. Got it. Wait, now I lost my click. What? Oh, okay. Could we write this more briefly? Okay. Okay, I'm gonna skip all of this unless y'all want to learn this. But this is... Wait. No, okay, never mind. I need to understand the letter part. Okay. The left-hand side of this equation contains 5 as a factor. Actually, I think reading it would be best. Okay. Could we write this more briefly? By the very meaning of an exponent, we can certainly write 5 to the exponent of 3 times 5 to the exponent of 3 times 5 to the exponent of 3 times 5 to the exponent of 3, which equals 5 to the exponent of 3, parentheses, to the power of 4. Numbers. We can go further. The left-hand side of this equation contains 5 as a factor times 12. The reason why is because the exponents are multiplied. So you can simplify that by just being 5 to the exponent of 12. This example is the essence of another theorem on exponents, namely if m and n are positive integers, then parentheses a m close parentheses to the exponent of n equals a to the exponent of mn. There is one more commonly used useful theorem on exponents. Suppose we wish to denote to blah blah, okay, whatever. It would just equal 2 to the exponent of 4 times 3 to the exponent of 4. Okay. Okay, that's... Wait a minute. AM...